Good morning, it's May 25th, 2018. I am starting on my conversation with Paul Gradenwitz, part 12, and we're discussing an article I have on SpoonfedRelativity website, which was written in 2012, where I did a calculation of the Schwarzschild metric and came up with two animations, well, multiple animations, this one and this one in particular. And I said, how would you describe what's going on in the animations on this page? And my question was, do you see these photons turning or not? He says, I think you are representing light as small bodies, photons. We are physically not able to add to the EM field an arbitrary amount of energy. We can only add it by quanta. We are also not able to physically remove from the field energy in an arbitrary amount, but only with quanta. So when we are thinking that in the field it remains as photons, but the EM field does not distinguish them. The amount of energy you take from the field in one quantum is not mandatory added to the field by one single quantum. So when you try to calculate the route of a single photon around a black hole, you run into trouble. And this is the trouble that I had with zero width photons. Um, you try to calculate the route of a single photon around a black hole, you run into trouble. You see the photons. And here, when I used the zero width, what I found was they slowed down, but there was no reason that they had for turning. It was only after um, I said, by the fact that their lower end is moving slower, it looks more like this. So in this situation, we actually added, I don't remember exactly what I did, but I think it was a matter of, well, I can go into the math here maybe a little bit. So the main thing that I did in both of them, where it did turn and didn't turn, was I set the left-hand side to 0, basically saying that no time actually passes for the photon itself. So its experience of time is 0. And so multiplying that through, I think I just left this in there. I also decided that I'm only going to look at um, the plane where theta equals pi over 2. Actually, I'll just go ahead and draw it down there. Theta, and so that is a right angle. Theta equals pi over 2. So I'm looking at this plane, a, a plane through the surface where theta equals pi over 2 and phi goes around that circle. So I think sine squared over 2 is 1. So just some canceling out. This is after this, and d theta is 0 because we're not changing theta. So in the next line, looks like this dr squared term comes over here, and this r squared d phi squared term comes over there as r d phi squared. And the left-hand side stays over, or the right-hand side stays over on the right-hand side. So this part is over here. Okay. Then in the next step, I just divided by dt squared. So I've got this thing, which is actually the radial velocity squared, and this thing, r d phi dt, which is actually the equation for the tangential velocity squared, is equal to 1 minus r sub s over r c squared. So that, so just to imagine the circle, the radial direction is that way. V radial is just dr dt, and the V tangential is r d phi dt. Oh, look at this. I think I've located the actual um, demonstration. Yay! Of course, I've got them under so many different names. Which one's the latest? Well, I can't use the dates because they're all April 19th at 5:53 a.m. So I'll just use the numbers and assume number 11 is the correct one to use. Just to get an idea of how long the code is. There's actually a lot of comments in here. I'll just scroll through it at the minimum level. Okay. And then we're down to the bottom. And you can see I've got an animation running down there. Oh, I was getting sophisticated in my Mathematica use back then. I had rotate and then I had usage. So I could actually request a reminder of the functionality on the thing. So rotate theta dot x comma y takes a Cartesian vector x comma y and rotates it counterclockwise by theta radians around the origin. And there's rotate. And then v colon usage. V returns vx comma vy, takes a position in units of Schwarzschild radii and angle as inputs. So that seems mysterious because I've got an x comma y in there and it wants the position in terms of Schwarzschild radii and angle. Why would I call those x and y? But yeah, v is a pretty big module with a lot of extra things in it. Okay, it actually calculates r from square root of x squared plus y squared. So it's taking x and y as the, I called them the Schwarzschild, takes a position in units of Schwarzschild radii. Oh, in units of. Okay, so x comma y are the coordinates, but they use the same units as the Schwarzschild radii, like meters or however Schwarzschild rate. Oh, so that means this distance here would be 1 Schwarzschild radii. The diameter would be 2 Schwarzschild radii. So if I give you number 3 comma 4, then it's 3 from the center. You would count over 3 to the right and 4 up. So that's what I was doing there. That's what that means. And then theta determines the angle for the photon. And then this calculates the required velocity for a photon at that position moving at that angle. So we start by finding Vx and Vy, which aren't going to be the final vector velocity. Vx0, Vy0 equals Vx, Vy. So that's going to be the same thing at first. R is the square root of x squared plus y squared. Theta xy equals, I think this is a number representing arctangent of x comma y. This is a special arctangent that goes ahead and takes two variables so that it gives you a full range from negative 180 to positive 180. Okay, just remembered I have tools at my disposal today that I did not even imagine when I was making this code. Like, I could make a video showing what I'm thinking. So Vx equals cosine theta, Vy equals sine theta. So, in other words, we've got, okay, let's say we've got this is our Schwarzschild radius. This point over here maybe is x comma y equals 3 comma 4. And then theta, that's 0. And this is, say, what, pi over 6. So, and we'll say the velocity of this thing is coming this way. And so, but that we'll define another theta. Theta being not pi over 6, but direction from there is going to be like pi. This is pi. This is pi. So we'll say that's 2/3 pi. 2 pi over 3. So Vx and Vy are going to be determined from this. Let's draw that in a different color. We'll make that purple. And this is Vx, whoops, Vx, Vy. And then I think theta Vxy is going to be identical to theta, which was an input of the thing, because pretty much we just said Vx Vy equals cosine theta sine theta. Theta Vxy is the arctangent of cosine theta sine theta. So yeah, you're going to get back theta here. On the other hand, theta xy is going to be related to this point here. So this is theta xy is this number here. Now, I must have had two different ideas of how to solve this problem, but option 1 was one of them, and I decided to call one of these V tangential and V radial. And what that did, okay, it rotated by theta xy, negative theta xy, so it moved this point over to here, or it didn't move the point, it just rotated the vector. It basically takes this vector and rotates that vector around that thing there, and then it will give a tangential velocity, which is coming this way in the phi direction, and a radial velocity, which is going that way. And so that changes this representation, which was in terms of velocity in the x direction and velocity in the y direction, to simply by rotating it over here, it turns it into a radial and tangential direction. Then it calculates theta v tangential radial. So you could imagine if this, let's see, this would almost entirely be in the tangential direction, but maybe a little bit in the radial direction. So the theta would be arctangent of tangential divided by radial. So it would be more, or if, well, let's put it this way. If it's this direction, the angle would be 0. If it's this direction, and the angle would be, what is it, pi over 4. If it's this direction, it would be pi over 2, 3 pi over 4, pi. So that would give, so then it says if v tangential equals 0, so if it comes out to be that direction or that direction, we're going to have an error because the tangential velocity is 0, probably because there's some division by error. And it says incline equals v sub r, vr over vt. So for this, for this vector, the incline would be positive infinity. For this vector, the incline would be positive 1. For this vector, the incline would be 0, negative 1, negative infinity. Okay, moving on. Apparently I had an option 2 there, but I didn't use it. And this is something important to discover. Vtan equals f of r c squared over 1 plus incline squared over f of r times sine vt. What is f of r? We'll figure that out in a second, but essentially we're figuring out a tangential velocity and a radial velocity, and then from this function, incline times vtan, and then recalculating a vx and a vy, which rotates back. Basically, it took this vx, vy, applied some function to it to slow it down, and then returned a vector in exactly the same direction as it started, but with a different magnitude. And so we're finding that different magnitude right here. So what is f of r? That's the key. F of r is just 1 minus 1 over r. Remember that the Schwarzschild radius in this case was 1. R is given in units of Schwarzschild radius, so that makes this be the same as the 1 minus r sub s over r in the Schwarzschild metric. So let's actually look at this equation here, where we were at the end of this, and compare that to this equation here. So all I'm going to do is basically solve for this term here, which is, but first I'm going to replace this with f of r c squared, and this with 1 over v radial squared over f of r, because this is inverse, plus v tan squared equals f of r c squared. So I will have vtan equals that's strange. I think I'm going to have to come both ways to get to this. That is vtan equals, or vtangent squared equals f of r c squared over 1 plus incline squared over f of r. Incline was v sub r squared over v sub t squared. Here I get v tangent squared equals f of r c squared minus v radial squared over f of r. So how do I make the case that f of r c squared minus v sub r squared over f of r is the same as f of r c squared over 1 plus v sub r over v sub t squared over f of r? For now, let's just say I do not remember exactly how this equation was derived. I do remember it being it was time consuming. I mean, not really time consuming to figure it out, but I think there were several days, maybe 2 or 3 weeks while I was thinking about this problem. And I was pretty excited when I figured it out, and I had absolutely nobody to tell that I had figured it out. It was just, and then once I did figure it out, all it did was slow down the photons, and it did not change their directions at all. In order to actually turn the photons, I made this other function called nextStatus. Do I have a, yeah, nextStatus usage, x comma y comma theta comma w comma t, takes a position x comma y and a direction theta and creates two photons a distance w apart centered at x comma y. The velocities and a new position of these two photons are calculated. Since these two velocities differ, this changes the final direction. So the final direction and final position is calculated. A thought, the spacetime interval between x comma y and x final comma y final may not be 0. So that means it was centered at x comma y, remember. So x final and y final was figured out um, from those things, from that center, two photons at equal distance, half a width to the left and half a width to the right from there. And then another thought, a straight space-time interval might not be zero, but is the curved space-time interval zero? So it looks like I actually had those outstanding questions at the time that I made this demonstration, um, whether it actually managed to keep that space-time interval